Well done. Okay, so here's kind of the next big thing that we need to figure out, and this is this process, and I emphasize the word process of dimensional analysis. So, in dimensional analysis, what you're doing is you're just looking at the units to see if the units make sense. So, this goes back to this whole idea that really understanding advanced sciences, and whether it's science, whether it's economics, doesn't make any difference. You have to be able to look deeper than the superficial idea of, oh, do I get an answer? So what dimensional analysis does, it basically gives you another tool to analyze mathematical relationships. So, and the reason I stress this is that, again, I want you to get out of this mindset that you just worry about a numeric answer. Okay? If that's all you're worrying about, you will never really understand any topic at all. Right? You have to be able to think through and see it through different windows, because the more ways you can look at a problem, the better off you can be. Now, invariably, usually at least once, if not twice a year, I get an email from former students going, wow, Bergkamp, you know, I was on a test in college, physics, chemistry, whatever. I didn't know how to work the problem. I just worked it using dimensional analysis, and I figured it out. Okay? Didn't know how to work the problem, but I knew if I made the units work out, I knew I at least had a chance to get the right answer. So this isn't something we're going to do today and then never talk about the rest of the year. This mindset needs to become a part of every problem that you do. Now, we're going to start off something with relatively simple, but we're going to build into something that's more complex. So here's the story. Let's start with something simple. Could I take 5 meters and add that to 2 meters? Could I do that? Why? What allows me to do that? They're the same units, right? Okay, hey, I get 7 meters. Could I take 5 meters and add that to 2 meters per second? Absolutely not. I don't know what I get, okay? So rule number 1 of dimensional analysis is that you can only add or subtract things that are the same units. Now, that seems like the most basic, rudimentary law that exists. But yet, ironically, this is the law that gets violated most. Because what happens is that when you get into these big complex equations, and you're adding things that first have to be multiplied together, and you're going to have like the wrong units on one part of it, and then your calculator, the oracle, will speak to you and tell you, oh, here's the answer. Woo! Hey, you write that down, and your answer doesn't make any sense because you actually tried to add together things that aren't the same. So this is why if you take that time and go, let me see what happens with these things. They're not the same. But literally, this is, even though it's the simplest, this is the one from my perspective that I see causes the most problems, because you all just want to write down numbers without the units, and then you try and end up adding things that aren't the same, and then I snarkily have to write on your paper, really? You added meters to seconds. Really? Okay? And then you all go, okay? Let's just avoid the, oh, man moments, okay? All right. But could I do this? Could I take 5 seconds and multiply that by 2 meters per second? Valid? I can do that. Why? I want to multiply it, okay? So mathematically, obviously, I get 10. Now, this is where this becomes more complicated, though. Because now you have to look at what happens with the units. And this is the heart and soul of this process of dimensional analysis. So when I take meters per second, and it's easier if you like stack these, because then it's easier to see how things cancel out. If I take 5 meters per second and multiply that by seconds, what do you get? Meters. So I get meters. So when you're multiplying numbers that don't have the same units, this is what happens in dimensional analysis. You're looking at this going, oh, okay, right, the seconds cancel out, I get meters. So when you multiply values that don't have the same units, what you get out of that is something completely different. So basically what you're doing here is that you're multiplying time by a velocity, and you're getting a distance. So you were multiplying two things that are dissimilar. You're multiplying a velocity by time, and then you get something that's even more different from that, because then you get a distance. Now, in contrast to that, if I were to take 6 meters per second and divide that by 2 seconds, could I do that all day long? What am I going to get? Why? So? So? Because you're multiplying by the reciprocal. So in this situation, because here's what's going to happen. You're going to look at this and go, oh, the seconds cancel out, and I'm going to get meters. Okay, the most common mistake that's made in this particular situation. This is what you're going to do wrong. You all sit there and go, Spur Camp, we won't do that. Don't be silly. So what's going to happen here is that that's just it exactly. If I take meters per second and multiply by that reciprocal, then I get meters per second squared, otherwise known as acceleration. So when in doubt in this process, when you're dividing, multiplying by the reciprocal is a really, really cool, subtle move to do. Because dimensional analysis is a process. You're showing how it works. Now, could I do this? Could I just take 2 times 6 meters? What am I going to get? 12 meters. Why do I just get 12 meters? Yeah, the 2 doesn't have any units. Basically what I'm saying is that, hey, I'm going to take 2 boards that are each 6 meters long, and I'm going to add them together, and I'm going to get a total of 12 meters. So if you multiply, divide, even if you were to take like the sine of 30 times 6 meters per second, random question, anybody happen to know the numeric value of the sine of 30?
1/2.
Huh? 1/2, beautiful, 0.5, okay? So the sine of 30 is 0.5. This, again, has no units, just the sine of 30. So if you do that, you're just going to get 3 meters per second, okay? Cool. Now, what if I did this? This is the stuff that we're going to do a lot. What if I were to take, question, 4 meters per second squared? Mr. Sharp, what am I going to get?
16 meters squared over the second squared.
Fantastic. Why?
Because you distribute the exponents all.
Beautiful. Okay? So what I'm saying is 4 times 4, that isn't the issue. That's going to be the 16. When I do that, then I'm going to take meters per second times meters per second. I'm going to get meters squared over second squared. Okay? Got that process. All right. And you do the same thing with square roots. So if you take the square root of 25 kilograms squared, you can take the square root of kilograms squared, and you're going to get 5 kilograms. Okay? So those are kind of your basic operations. So let me hand out the assignment, and we're going to kind of work through this together. Okay? So
Miserable. Somewhat. I remember signing for something. And then my tangent to 1. And that's what I remember. I don't remember.
okay, like I said, this is one of the few instances where we're just kind of piecemeal this together in class. So, up there at the top, you're going to list the units, not the variables, okay, the units that you're going to use the MKS system to measure these different things. So, distance, let's get everybody started the same way. Distance is going to be in meters, okay? Mass, newtons or kilograms? Kilograms. If I wanted, now if I said weight, which would be force, that would be newton. Mass is going to be kilogram. Now, on the force, because this is going to be important later on the force side of it, what are your two options for force? Newton is one of them, okay? Just put a capital N, that's cool, okay? You can do newtons. Now, if you do the smash mouth physics, because force is mass times acceleration, what's the other way that you can do force? Kilograms, meters per second squared, okay? Notice that the only thing that's down below that line is the second squared, okay? So it's kilograms, meters per second squared. So then on those rules, that's just what we kind of went over, okay? So all that middle section is a summary of everything that we've just talked about, okay? Not a big deal there. Now, when you get down to that about 2/3 of the way down, you have number one, and I've given you VT. So when you do dimensional analysis, what you do, you don't worry about numbers, okay? Your calculator will do you no good on this assignment, okay? No good. Don't take your calculator out. It won't do you any good. So what you do, and we're going to do this on basically every equation that we're going to look at. The first thing that you do is you substitute in the units that this thing is measured in. So you have VT. So velocity is measured in meters per second. So I'm going to take meters per second, and then I'm going to multiply that by time, which is going to be in seconds. So then the seconds cancel out, and you get meters. So what we're saying is that if you multiply velocity by time, you get a distance. So you're multiplying two different quantities, and then you're going to get a third quantity that's different from the first two. So you're multiplying a velocity by a time, and you're generating a distance. Now, let's talk about number 3. You have AT. So, acceleration measured in meters over second squared. I want to multiply that by seconds. So, I like to stack these vertically. If you write them like, this is what I've seen. If you try and do meters per second squared times seconds, I've seen this go south where kids will do this and they'll go, oh, I get meters per second cubed. Okay, because they look at this as being like kind of multiplied on the same line. I've found that if you stack them, that reduces that error. Okay? You don't have to, but I'm just saying if that reduces that. So when I take meters per second squared times seconds, I lose one of those, I get meters per second, otherwise known as velocity. Now, on number 4, and this is why I kind of put these side by side. On number 4, you have AT squared. So then you got meters per second squared. But then I'm going to multiply that by second squared. So what's going to happen to my second squared? Well, it's going to cancel out, and you're left with meters. So here's what I want you to see. If I multiply acceleration by time, I get a velocity. If I multiply acceleration by time squared, I get a distance. Okay? So in both situations, I'm multiplying acceleration by time. But in one situation, I get a velocity. In another situation, I get a distance. Okay? Now, that last one, you have m times m. In this situation, is the m representing meters, or is the m representing mass? Mass, because it's a variable m. So this is a calculation that we're going to do a lot when we get into gravitational fields, okay, to calculate gravitational attraction between two objects. Okay, it's mass times mass. So you're going to have kilograms times kilograms, which is going to get you kilograms squared. Okay, so your answer number 5, kilograms squared. So you got a couple questions to answer right there. Multiplying by a fraction of whole number changes the units, which is scoring it. Those are just yes or no answers. Okay. Now, here's the heart and soul of what we're going to do. And I'm going to work number one with you to make sure everybody's cool with what I want done. So I've got V equals V naught T plus A. Okay? So this sounds very sciencey. It's like, hey, what'd you study in physics today? Oh, we studied how to describe motion. Really? Cool. What equation did you come up with? Well, V equals V naught T plus A. You sound very scientific. Like if you're at a party, and you'd have to be really desperate for this, but if you're at a party and someone says, hey, what classes you got? Oh, I'm taking physics. Really, what's your favorite equation? V equals V naught T plus A. Okay? And if that's what you're saying at a party to sound cool, whoa. Times have changed. Huh? It could come up in conversation. So this sounds good, and it looks good. It looks like a good equation. But what you do in dimensional analysis, and this is what we've been leading up to, now you're going to look at this and go, wow, does it actually work? Okay? This is the crux of this. So, first thing that you do, put in all the units for everything. So this is a compilation of everything that we've done. So you're just going to come here and go meters per second. Now, what's the difference between V and V naught? To V or to V naught? That is the question.
Initial.
V naught is the initial. Is everything still going to be in meters per second? Absolutely. So then I've got meters per second times seconds plus an acceleration in meters over second squared. So I got meters per second. When I multiply this together, the seconds cancel out. I get meters. So here's the question, my esteemed fellow students. Can I take a distance and add that to an acceleration and get a velocity? Absolutely not. So this equation looks cool, but is it valid? No. Okay? It's not a valid equation because of the fact that at the end of the day, you're trying to add a distance to an acceleration. As you say out on the farm, that dog won't hunt. Now, but here's what will happen. Mark my words. What will happen is that if you're actually working this in the context of a problem, if you solve that equation incorrectly, you just put in numbers, and you actually put in like 10 times 5 plus 15, and all you do is just write down the numbers, mathematically, your oracle, your calculator would generate an answer. And then you would say, oh, I get a velocity of meters per second. And if you had written down the units along the way, you would look at that and go, wow, that is not going to work. But this is why you have to go beyond just using numbers, okay? You have to embrace this idea of going, wow, how does this process actually work? Because we're going to, especially once we get into AP Physics 2, okay, if you're going to ride that train, you're going to be doing some horribly, horribly complex equations, especially when you get into like magnetic fields and that type of thing. And the sooner that you embrace this idea of paying attention to the units, the better off you're going to be. Okay, on the back side, I'm going to get you started on some of these. So on number 2, you've got time equals V divided by X minus X naught. So again, here's your process. Put in the units. So I'm going to have seconds, meters per second, divided by meters minus meters. Now, here's what I don't want you to do. Okay, this is what I do not want you to do. If I take meters minus meters, do I get 0? No. Okay? All I'm saying is that I can take some number of meters and subtract some number of meters. If I take some number of meters and subtract some number of meters from it, what units do you still get? Meters. So what I would do is I would regroup then and go, okay, that's meters per second divided by meters. Okay? Now, if it were me, I would not divide by meters. I would multiply by the reciprocal. Okay? This is a process. We are so far away from Christmas and the season of miracles. What you cannot do is just write this down and go, oh, everything cancels out and it's valid. Yay. This is a process. You show how things cancel out. All right? When you get to number 3, this is an equation we're going to use a lot. Technically, it has a name of that equation. So you have x equals v squared minus v naught squared over 2a. When you're doing number 3, and you have that 2a in the bottom of it, don't even worry about that 2. It is not going to change the units, okay? So when you get like a number 3 where you have that 2a, you have the same thing on number 4 where you have that 2 underneath the radical, don't worry about those numbers. Just leave them out when you're doing dimensional analysis. Do you need to worry about them numerically when you start crunching numbers? Absolutely. Okay? But not when you're doing dimensional analysis. When you get down to number 7, okay, you have time equals mv over force. On number 7, do not put newtons, okay? That is just going to lead you to pain and suffering if you put in newtons. On number 7, what I would recommend on that force, put in the kilograms meters per second squared. Okay? And then what I would do is I would multiply right away by that reciprocal because you have that big ugly thing underneath. When you get to number 9, this is the equation to determine the period of the pendulum as it oscillates back and forth. 2 pi square root of L over G. I tell you L is the length of the pendulum. What's that going to be measured in? Meters. You have G, which is the gravitational acceleration. What's that going to be in? Now, I don't want the number, just the units.
Meters per second.
Meters per second squared. Okay? So on number 9, you're going to have meters over meters per second squared. Okay, so do this right now. So I'll give you some time to work on this. If you're not sure if you're doing it right, ask me. I will tell you, okay? And if you go, man, am I showing enough steps? Show it to the person beside you. If they look at that and go, I have no idea what you're doing, I probably won't either. When in doubt, show the steps, okay? So make that happen. All right, stop me on the camera.
This is our